So let's talk about power series. Again, when I say power series, what I mean is that someone is coming up to you, possibly me, possibly someone on the street, and handing you a series that looks like this one, for example. So this was a series we were looking at before we took the break. A series whose terms are built out of powers of x to the n. And I've had Mathematica kind of be a little bit more brutal about, instead of writing x minus 0, because again, this number right here tells us the center point of our power series. So in this particular example, because we were building everything out of powers of x to the n, we're thinking of the center point of our series as x equals 0. If this was x minus 1 or x plus 4 or something, then we would have a different center point. But that's the first thing we want to know about our power series, is what is its center point? But then it's built out of these powers by multiplying each of them by a coefficient. And those coefficients, at least in the example we were looking at before the break today, those coefficients followed a pattern. Negative 1 to the n plus 1 divided by n. So again, if we were to write out the terms of this power series, the first, and I should really make this n equals 1 as the beginning, the first would be negative 1 to the second power over 1 times x minus 0 to the first power. So that first term is just x. The term when n is equal to 2 is minus x squared over 2. In other words, minus 1/2 x squared. Maybe I'll write it that way this time. Minus 1/2 x squared. The next term for n equals 3 is 1/3 x cubed. The next term for n equals 4 is minus 1/4 x to the 4th. But the virtue of writing it with the summation notation is that now we feel free, or should feel free, to write as many terms as we want to and let this tend to infinity. And once we have an infinity upstairs, now that makes this a series instead of a polynomial. So that's the only difference between the polynomials we were looking at before the break today and the series we're looking at after the break, is that this limit on top of our sigma is now infinite. So we want to think about what happens to this function as we add infinitely many terms to it. How does it behave? And we have two questions to answer there. First of all, for what values of x does the series converge? That's going to tell us what is the domain of this power series as a function. And instead of domain, when we're talking about power series, we tend to phrase that as the interval of convergence. Where does x have to live in order that this be a convergent power series? That's the first question, and that's the one that usually takes the longest to investigate. And the ratio test is our tool for how to investigate the answer to that question. What we'll find out is that a lot of the answers to these questions about power series are answered by the series of their coefficients. So if I say coefficient series, what I mean is this same power series just with the powers of x taken out. Negative 1 to the n plus 1 over n added n equals 1 to infinity. So for example, we could take this coefficient series and we could answer questions about it based on what we did last week. Namely, as a series of real numbers, we could answer, is it absolutely convergent, is it conditionally convergent, or is it divergent? And the answer to that question turns out to bear on the answers to our questions about power series. So if I say coefficient series, that's what I mean. Just take out the powers of x and think of it as a series of real numbers this time. And the second question, the second task that we want to be able to do with our series is to treat them as functions. In other words, everything that we could do with a function which we know by name, which we know by an algebraic formula like f of x equals e to the x or something like that, how can we do those same operations? For example, composition of functions, addition, subtraction, and multiplication of functions, calculus like derivatives and antiderivatives with those functions. Can we treat power series the same way? In other words, this power series is describing a function for me. Can I find a power series that would represent its derivative? Can I find a power series that would represent its antiderivative? Can I find a power series that represents g of 2x or g of x minus 4 or something like that? So turning one power series into another power series in order to turn one function into another function. We'll see what some of the uses of that are today. But these are our two tasks. First of all, where does this power series converge? What is its interval of convergence? And second of all, what else can I do with this power series if I treat it as a function? Let's gather some evidence on how this particular power series behaves. Right now, we're not looking at the power series in total. We're just looking at its first term. So if I want to understand what it does as n tends toward infinity, I have to add some more terms into it. So here's the power series with its first two terms included. So here's the series with terms up to third order included. By the way, this was a third order polynomial that one of your groups came up with as a Maclaurin approximation to a function whose name we knew before. But now we're proceeding on the assumption that what we're looking at is a series. We're not looking at it as coming from some other known function, that we're just building whatever series we want to build. And so if this is a series that I'm building, here is its third partial sum. Here's its fourth partial sum. Here's its fifth partial sum. And the further out that we go, more and more partial sums, we find out that something happens. Yeah, we get kind of this little propeller action going on here at the end, right? So here what we're looking at is the 50th partial sum of this power series. In other words, this graph that we're looking at on screen right now is the graph of the partial sum, which looks like x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4 dot, 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 dot. And the very last term we have here is actually minus x to the 50th over 50. But what we're finding out is that even though some things are kind of changing as we move from one partial sum to the next, there is a place where not much is changing. What's the difference between the 49th and the 50th partial sum? Here's the 49th. Here's the 50th. This is like an eye test now. Better 1 or 2? What's the difference between these two? Right. So the biggest difference between these two is what's happening with end behavior. The 50th partial sum looks like it crashes down to negative infinity. The 49th partial sum looked like it was going up to positive infinity. So that's what's different about them. But what seems to stay the same about these two partial sums? At least as far as we can tell. Well, okay, so yeah, one of the things that seems the same is that both of them are sort of escaping out to infinity, either positive infinity or negative infinity, once we cross that threshold right there. But to the left of that threshold, they look pretty similar. So this is the part that stays the same. This is the part that seems to blow up. And so let's make a hypothesis here about this series. And the hypothesis might be that once we cross this line, and this line looks like it's at x equals what? On this graph. It looks like x equals 1. So the hypothesis is that if x is to the right of this line, then what do we think the series is doing? Diverging. So there's a hypothesis that we're going to test. What about if x is less than 1? If x is less than 1, then the series is taking on these finite y values over here. So if x is less than 1, we might equally well predict that this series is converging. And this is a hypothesis on the domain of our function. Really, secretly, that's what we're making a hypothesis about. Because if our series is diverging, that means that g of x does not have a finite value for x greater than 1. So g of x would be undefined for x greater than 1. But if we claim that it's converging for x less than 1, we would be saying that g of x has a value, has a finite value, and so is well defined for x less than 1. If this is our hypothesis, how might we endeavor to investigate or to prove this hypothesis? How do you, based on your reading of section 10.6, how do you determine where a power series converges and where it diverges? If this is my series, and I think of having an infinity up here instead of a 49, how do I figure out whether or not this series converges or diverges? let's take a moment and just pick on the pieces, the factors that make up this power series. Down here in the denominator, I have a factor of n. Where does that belong in my order thermometer? It's a polynomial piece. So my n is living somewhere in here. But then I also have another piece, the piece out here, x to the power n. Where does x to the power n live in the order thermometer? Exponential. Because the n is upstairs now. To the n. So in other words, what the order thermometer is telling us in this example is that it's the x to the n that's going to determine the convergence or the divergence of this series. And the n out in front, usually at least, is going to have less power, less order, if you like, to determine whether or not this is a convergent series. But the answer to the question is going to depend on the value of x. But because there's an exponential factor in here, what's the tool that we think is going to get us the answer the most efficiently? What convergence test is most appropriate here? Ratio test. Anytime we have a factorial or a power with an n upstairs, a geometric factor, an exponential factor, the ratio test is the most appropriate tool to investigate the convergence or divergence. Let's see how the ratio test gives us that answer. So what I'm going to do is again set up the ratio, the nth ratio, which we called rho sub n, of our series, which this time I'm going to preserve the absolute value in it. And it's the n plus first term of our series divided by the nth term of our series, that ratio taking an absolute value. But this time, the n plus first and nth terms of our series each have an x in them. So this whole thing here is our nth term. So my denominator, absolute value of, my denominator has negative 1 to the n plus 1 divided by n times x to the power n. So my denominator has an x in it. My numerator will as well. The n plus first term is obtained just by replacing every n that we see with an n plus 1. And so is negative 1 to the n plus 1 divided by n plus 1 times x to the power n plus 1. So the first point is, when we apply the ratio test to assess the convergence of a power series, that x, which is part of our building block, that x comes along for the ride. So we're just going to include the x in our ratio calculations, because x at this point is a variable. We don't know what its value is. But the requirement that we want this series to converge will define for us what values x may have at the end. To get there, though, we need to simplify. So let's keep going here. So this is the step that consumes the most of your energy when you apply the ratio test. First of all, when I take the absolute values, my negative 1 to the n plus 1 and negative 1 to the n plus 2, both of those are going to become positive 1. So those we can just forget about. Also, I have in the denominator an n plus 1 and in the numerator an n. That's coming from these two factors, that n and that n plus 1. I'm going to make those into their own fraction out there. And since they're both positive, we can keep them outside of the absolute value. Then I have inside of my absolute value, in the numerator, an x to the power n plus 1, and in the denominator, x to the power n. And now is the most crucial step of all. What happens when I divide n plus 1 powers of x by n powers of x? I get a single power of x. After all, when you divide powers, you subtract their exponents. N plus 1 minus n gives me just 1. So when I divide these powers of x, I get just x. So this is the nth ratio of our power series. And the ratio test tells us we don't want just the nth ratio, we want the limit of those ratios as n tends to infinity. So now we'll take the limit as n goes to infinity of this thing. And what happens to n over n plus 1 as n tends to infinity? L'Hopital? Anyone? Just becomes 1. So in total, my limit is 1 times the absolute value of x. Because after all, x isn't part of the variable that's tending toward infinity here. N is tending toward infinity. X is just hanging out. So when I take this limit, I still have an x in it. In fact, my ratio of this series, my asymptotic ratio, is equal to the absolute value of x. So, if the question is, what values of x make this a convergent series, then what does the ratio test tell us? What does the ratio have to be in order that our series converges? It has to be less than 1, and it also has to be, technically, it would have to be bigger than negative 1. But because our ratio is always positive, because we take the absolute value before we tend it to infinity, this is really all we need. We need the ratio to be less than 1 in the ratio test in order that we have a convergent series. But our ratio is what we have down here at the bottom, the absolute value of x. And so because our ratio depended on x, the ratio being less than 1 depends on the absolute value of x being less than 1. And if the absolute value of x is less than 1, how do we solve that inequality for x? What does x have to be less than if its absolute value is less than 1? Remember, the absolute value of x is either equal to x if x is positive, or it's equal to the opposite of x if x is negative. So if x is positive, its absolute value being less than 1 is equivalent to x being less than 1. If x is negative, then its absolute value being less than 1 is equivalent to x being greater than negative 1. So that's another thing to do in this section, is maybe review how to solve inequalities with absolute values in them. But if we do that here, we find out that our series converges, definitely converges, provided x is between negative 1 and 1. And that's part of the behavior that we saw here, right? That as long as x was less than 1, it looked like the values of our power series were pretty well defined over here. But as soon as we crossed x equals 1, suddenly it almost looks like a vertical asymptote right here. And a vertical asymptote is exactly what we would have if we could see all infinite the many terms of this power series. So after we cross that vertical asymptote, no longer is this a convergent series. But now here's a question. What about x equals negative 1? Kind of again looks like we have this weird behavior happening down here, such that when I cross x equals negative 1 to the left, it also looks kind of like a vertical asymptote on that side. So the last thing we want to do to finish this example is, now that we know that this power series is defined for values of x between negative 1 and 1, and is definitely undefined for any values of x that are greater than 1 or less than negative 1. So let me clear out some space here and emphasize that conclusion. Because if this ratio is bigger than 1, then we know that the series diverges for sure. Diverges if the absolute value of x is greater than 1. So if x is greater than 1, or x is less than minus 1. But this leaves out two cases that we have to check on our own. There's two values of x whose convergence or divergence the ratio test has not answered for us. What are they? 1 and negative 1 are endpoints. So in other words, this inequality here defines for us an interval on the real number line, the interval from minus 1 to 1, exclusive of both. And the question is that the interval on which we have a convergent series? Or might our series also converge at one or the other of those endpoints? So the second step, now that we've figured out with the ratio test the extent of our interval, let's check the endpoints manually. In other words, I'm going to plug in those values, x equals 1 x equals minus 1, into our power series and figure out what we have at those places. So if x is equal to 1, we're looking at the power series summation negative 1 to the n plus 1 over n times 1 to the power n running from 1 to infinity. And now this is just a series of real numbers. In fact, since 1 to the n is equal to 1, that's what our series looks like. So at x equals 1, this is what our power series is. And my question to you is this power series, sorry, not a power series, is this series of real numbers convergent or divergent? Let's apply the sorting hat. Do its terms go to 0? Negative 1 to the n plus 1 over n. Do those terms go to 0? Yeah. They do. Negative 1 to the n plus 1 alternates sign, but the n downstairs goes to infinity, making the terms go to 0. So that's good. It passes the divergence for dummies test. Is it an alternating series? Yes. It's an alternating series. So what can we say about this series if we know that its terms go to 0 and that it is alternating? It's at least conditionally convergent. But at this point, we can actually stop, because all we cared about here was, does this series add up to a finite value? And the answer is yes, because it's an alternating series whose terms go to 0. It's convergent, which means that not only is our power series defined at x equals, from x between negative 1 and 1, but it's also defined when x equals positive 1. So we're going to include x equals 1 in our interval of convergence, because when x is equal to 1, this power series has the value summation of negative 1 to the n plus 1 over n, which is a convergent series. Now, it's convergent, albeit conditionally, but it is still convergent. And so x equals 1 becomes part of our interval of convergence. And so up here, I'm going to include 1, the right endpoint of our interval, as part of the domain of our power series. Then the last thing we need to do is figure out, should we also include x equals negative 1? At x equals negative 1, our power series is negative 1 to the n plus 1 over n, there's the coefficient, times x, which is now negative 1, to the power n running from 1 to infinity. And this is, again, a series of real numbers. But this time, negative 1 to the n times negative 1 to the n plus 1, we can combine those two powers together. It becomes negative 1 to the 2n plus 1. But if n is an integer, then what kind of an integer is 2n plus 1, even or odd? 2n plus 1 is going to be odd. So upstairs, I'm raising negative 1 always to an odd power. What's negative 1 raised to an odd power? Negative 1, right. So this time, our series is the summation of negative 1 divided by n. We can take that negative sign out in front if we like. But again, we're asking the question, does this infinite series converge or diverge? We have minus the sum of 1 over n. The terms go to 0, but it's not an alternating series. What is the summation of 1 over n? Divergent because it's a harmonic series. It's the polynomial series with p equals 1, which we showed by the integral test was divergent. So in other words, because of that result, we cannot include x equals negative 1 in our interval of convergence. And so our final answer for what is the domain of this power series, what is this interval of convergence, our final answer is that it is x between negative 1 and 1, inclusive of 1, the right endpoint, but exclusive of negative 1.